polyprotic acids are acids that can produce more than one hydrogen ion in solution. Now, the prefix poly means many, and technically protic refers to proton, but if you think about it, here's like a hydrogen atom. A hydrogen atom only has one proton in the nucleus and one electron in its first energy level. So as a +1 hydrogen ion, we are just losing that one electron. This guy's gone. So a hydrogen ion really is the same as just a proton. So polyprotic, meaning many protons or many hydrogen ions that can be produced in solution. Now the biggest takeaway here is that, let's say I'm looking at phosphoric acid, H3PO4. There are 3 hydrogen ions that can be produced in solution, but they're not all produced at once. So it's not like saying I have a 1 molar solution of H3PO4, I'm going to get 3 moles of hydrogen. Each hydrogen comes off with its own Ka value. So there's a tendency for each hydrogen to be produced in solution. Now when I look at the 3 Ka values for the 3 hydrogen ions of phosphoric acid, right away I notice that they're all small. They're all less than 1. So they are all weak acids. And so the first hydrogen comes off and the Ka is 7.5 times 10 to the negative third. Then I'm left with this guy, the dihydrogen phosphate ion. That guy could give away another hydrogen, but the tendency is quite a bit smaller, 6.2 times 10 to the negative 8. Well, then that still leaves me with the hydrogen phosphate ion, which does have a hydrogen ion that it could produce. But look at how small that K value is. Ka3 means like the 3rd hydrogen produced. The Ka now is only 4.8 times 10 to the negative 13th. Here's one other thing we should mention. Remember that equation Kw equals Ka times Kb? So that Ka, like say I'm looking at Ka3, that's in reference to this guy, the hydrogen phosphate ion. Well, here it would be its conjugate base, the phosphate ion. It's a negative ion, so we've always said that negative ions make me a little nervous, that they could act like bases and take hydrogen. Let's say we would calculate the Kb for phosphate. We'd say Kw is about 10 to the negative 14th. And let's just estimate. So I'm going to estimate that the Ka for the hydrogen phosphate is about 10 to the negative 13th. And I want to solve for the Kb of phosphate. So the Kb of the phosphate minus 3 ion is approximately, what, 10 to the negative 1st? Which it's still small, but it tells me that the phosphate ion is a pretty good base, that it's really attracted to hydrogen. That's why the Ka3 is so small. It's that the hydrogen right here is so attracted to the phosphate ion. That phosphate ion does not want to let go. So again, often the conjugate bases of weak acids have a pretty strong attraction for that hydrogen. That's why they're weak acids in the first place, that those negative ions are really attracted to the hydrogen. Another example of a polyprotic acid, a very common polyprotic acid, is sulfuric acid, or sometimes we might call this one diprotic, meaning that there are 2 protons or 2 hydrogen ions that can be produced in solution. And again, they each have their own Ka value. They don't just puke out into the solution at once. They come off one at a time. But now compare these K values. Ka1 is large, it's greater than 1. meaning that this is a strong acid. H2SO4, sulfuric, it's a strong acid, but only the first hydrogen dissociates 100%. Because then when I look at the second dissociation, I've got the hydrogen sulfate ion, and now its Ka is less than 1. So the hydrogen sulfate ion is a weak acid. So if I had, let's say, a 1 molar solution of H2SO4, by far that first dissociation is going to give me way more hydrogen than the second. The first is strong. So if I wanted to do the pH, I can really just say opposite log of 1. The second dissociation, being weak, is not going to contribute a significant amount of hydrogen, just the first step. And you don't have to memorize this. They're going to give me the K values. Or even in phosphoric acid, the first dissociation has the largest K value. So the first dissociation, whether it's strong or weak, will always be the more significant source of hydrogen. And so if I wanted to calculate the pH of a phosphoric acid solution, I could set up a weak acid ice table, but I only need to do one. I would just do an ice table with this first equation and the first Ka. Now, thankfully, we're not going to have to solve for pH of weak polyprotic acids, but we should just know that based on their Ka values, the first dissociation is always the most significant source of hydrogen.